Good afternoon, class. In today's video, what I wanted to do is to talk about the Doppler effect. So in this video, what I'm trying to do is to pull out my artistic skills a little bit and try to draw an ambulance and a person. So if you will forgive me if they're not the most artistic things you've ever seen, but they are what they are, just to get the point across. So the Doppler effect works like this. What happens is you've got a source of sound, so in this case it's going to be the ambulance, and what you do with it is you have the source move, or you have the observer move towards or away from each other. So in this case, in this example here, the ambulance is moving this way, and the person is stationary. The person can't. So this will be henceforth known as the source, and the person will be henceforth known as the observer. So if the source is moving this way, the observer can be stationary, or the observer can be moving this way or this way, towards the source or away from the source. So those are the several ways that this can occur. Now, of course, can this ambulance be moving away from the observer as well? Yes. Usually, in the case of these types of scenarios, it would be that the ambulance or the source is on the road and it passes the observer, and once it's past the observer, it's going from the ambulance is going towards the observer to away from the observer. So I wanted to just point out like the directionality of what's going on. The whole reason for that is that it's easier to picture what's happening. If you want to even try to imagine this, it's kind of like when you're for me, this happens to me a lot. I'll always hear the Doppler effect when an ambulance passes by on the freeway. Let's say I'll be stuck in traffic and the ambulance will be coming by in the opposite direction. So I'll be going this way, the ambulance will come this way on the other side of the freeway, and I'll hear the ambulance get higher and louder as it comes towards me, and then lower and softer as it goes away from me. So those are that's one of my real life examples of how I can feel this effect. Now, of course, why does this occur? Why do we have this thing called the Doppler effect, and why is this? Why does it change the frequency? And of course, the other question is it even a real effect, or is it just all psychological, all in our heads? So here's the answer to that last question. It's not all in your head. It is actually a real effect. Here's what's happening, because you have to understand, when instead of thinking of the source or the frequency from the source, in this case the ambulance, instead of thinking of it as this continual like beam of sound that comes out, what you might want to think of it as something that is pulsing. So the sound that is being emitted by this by the source is leaving the source, and it's going out at the speed of sound. So if the source moves, you've got one pulse that goes out like this, but then the next pulse will start over here because the source was here, now it's here, right? So it starts here and sends out a pulse, then it starts over here and sends out another pulse. Both of those pulses were moving at the speed of sound. One of them, though, because the source is moving in this direction, the ones in front over here are going to get smashed together. And so if the sound gets smashed together and it looks like it becomes compressed because of the moving source, then what the observer is going to hear is that the sound is going to increase in pitch because the frequency is going up. Likewise, on the other side, as the source moves away from the spot where it initially sent out that sound pulse, what happens is those pulses get spaced further and further away from each other, and if they get spaced further and further away, when we hear it, it sounds like that frequency is going down. So that's how you can imagine what the Doppler effect is like, and of course why when it's coming towards you it starts to get louder and higher in pitch, and when it passes you, it's now becoming lower and softer. So those are the two ways to think of it. Now, that's kind of the intro to all of this, and of course there's an equation that governs all of this. What I did want to do was to start with an example problem to help you out with this one, and then I'm gonna do another video where I take this exact example problem, but I make it a little bit harder because there is a second layer to this, to these types of problems that can get much harder. So, I thought I'd do that, but I'll save that for a second video because one, it's a lot. It'll be a lot of information, and two, there's not enough board space to actually put that second example in. But the next video will be more of a, not really advanced, but definitely an intermediate level problem because it's what I would like to call a two-step problem. So if you ever want to see what a two-step problem looks like and how that can actually become quite challenging for physics students, stick around for the next video. You'll see what I mean. So in this case, what I wanted to do is to first show what the equation is for the Doppler effect, and that's going to be the frequency the observer hears, that's why f sub o, is equal to v plus or minus of v sub o all over v minus plus v sub s. Now, of course, you might be, legitimately wondering, wait, but why is it plus minus over here and then minus plus over here? Are they like opposite of each other? And the answer is actually yes. Because one is in the numerator and one is in the denominator, the sign that it takes is actually going to be very important. So if you want the frequency to go up, then in this case you want the denominator small and the numerator big. That's why plus is on top and minus is on top over here. And if you want it to go down, you want the frequency to go down, you want the denominator as big as it can be and the numerator to be as small as it can be. So that's the two ways that this can work. And of course all of that times the frequency that the source is emitting. Now, of course, what is v? Well, v is the speed of sound. And this is, of course, now hopefully you remember this from my other video on sound. This, if I don't give it to you, you're going to have to figure out for yourself. So be careful with that. That's where the two-step problem comes in. But in this example, I'm just going to give you the speed of sound. I'm not going to ask you to calculate it because otherwise that would be a little bit more difficult type of problem. So the example is you've got an ambulance that's moving towards you / away from you at 20 meters per second. I'm going to pause right there and to point this out. Notice I wrote this question out in green, but I have the word towards and away from in two different colors, blue and red. There's a reason for that, and that's because when I split up the work, instead of having to rewrite this entire problem, I'm going to do the blue work, which is that's going to assume that the question is saying the ambulance is moving towards you. That would be blue, and if I read the question again, that says an ambulance is moving away from you, that'll be in red. So I wanted to show that, just so that you get an idea that I'm actually doing two different problems, just from two different perspectives based on the Doppler effect. Okay, so the ambulance emits a frequency of 300 hertz. If you are stationary and the speed of sound is 340 meters per second, what frequency do you hear? So basically it's saying, what is the frequency of the observer? So we don't know what that is. We know the frequency of the source is 300 hertz. We know the speed of sound is 340 meters per second, and that the speed of the source is 20 meters per second. And so now we're going to do this problem two different ways based on the two scenarios that I gave right over here. So we plug this in. We note that stationary means that the velocity of the observer right over here is 0. So that's why I didn't write anything here. I just wrote v instead of v plus or minus v sub o, which is just 0 anyway. So it's just going to be v over v minus v sub s, all of that times f sub s. And that's nice because we have all the numbers that we need for this. So 340 over 340 minus 20, all of that times 300, and that gives you an answer of 318.75 hertz. One thing I do want you to note is that as this source is moving towards the observer, the sound actually does, physically, the frequency does go up. It gets higher in pitch. Whereas if you were to, once it moves away from the observer, the sound gets lower. So how do we do this if it's moving away? Well, the equation changes a little bit. So instead of it being minus, it's going to be plus. Okay? And this is also, by the way, detailed out in the reflection questions for the Doppler effect and in the notes for the Doppler effect. So just in case in case you're like, well, how do I know it's minus and how do I know it's plus? I do detail out the differences and how you know when to use which sign. So when it's moving away from you, everything's going to be the same except it's v plus v sub s instead of v minus v sub s. So we plug in all of our numbers again, and then we find out, like, pretty much expectedly, that the frequency of the observer is going to be less, because now this, instead of the denominator becoming lower than the numerator, it's becoming bigger than the numerator. So therefore, you're going to get a smaller number, 283.3 with the line over it, or 283 and a third, approximately hertz. And now some of you might be worried or wondering, I should say, why did I use decimals? I thought you hated decimals. That'd be the natural question to ask. And the reason I did that was because this one, it was actually a nice even. You're right. I could have left this as a mixed number or an improper fraction, but this came out to a terminating decimal. So I thought, oh, okay, I'll leave it as a terminating decimal, because those are actually okay in my book, at least in terms of my personal taste. This one, on the other hand, is not a terminating decimal, but it is something that you can deal with because of the 3 with the line over it. So if you just say, oh, okay, well, they're close enough, and they're both decimals. This one is not so crazy. It's just you kind of know what to expect with this answer as well. I left them both as decimals instead of trying to keep them as improper fractions. So thought I'd just point that out, make sure that to address that just in case anybody had a question about that. So that concludes how to do these two example problems about the Doppler effect. In the next video, what I'm going to do is I'm going to do this exact same problem, but instead I'm going to flip this around and make the ambulance stationary and you, the observer, moving as well. And then in the third installment of this, for this exact same example, I'm going to have you figure out what the speed of sound is. So look forward to those next few videos. So that concludes this video. Good luck in your studies, and may the force be with you.